All right, our last session before lunch is titled Secure Your Code Via AI, presented by Kanal. Eli Kanal is a technical manager at CERT, focused on applying machine learning techniques to the cybersecurity domain. His team has contributed to a wide variety of projects, including malware classifiers, cyber attack forecasting, and automatic vulnerabilities analysis. He also functions as one of SEI's experts on blockchain technology. Prior to joining CERT, Kanal worked at Highmark Incorporated. He led a team of analysts and statisticians in providing data and statistical analysis for the entire health plans operations division. He also worked at PNC Bank as a quantitative analyst in the corporate risk department and as a postdoctoral fellow at Carnegie Mellon University, studying behavioral neuroscience. Eli earned his PhD in biomedical engineering from the University of Pittsburgh, focusing on neural signal processing. He is a member of the IEEE and the AAAI. Please help me welcome Eli.
All right, hello. Looks like we got quite the room so far, so that's great. We'll see if people trickle in. But anyway, so today I wanted to give you guys a bit more of an in-depth walkthrough. So we've kind of gone through before. We saw some talks just giving general overviews. We had some talks about what's going on locally here in the city. In this talk, I wanted to go a little bit more in depth and really talk some of the guts about how you can secure your code in AI. This is going to be going through some of the techniques that we have. So let's walk this through here. You already saw this slide earlier. I actually work for Mark. I work in Mark's division. The only thing I'll mention here is that our team actually focuses on applying ML and AI to all the stuff that goes on at CERT. So there's a whole lot of techniques that we use at CERT to prevent all sorts of bad things happening, all sorts of cybersecurity applications. So if someone's building a malware detector, we'll help them build a classifier. If someone's doing a network analysis, we'll help them build the network analyzer and machine learning techniques to apply to that concept. So we'll move on from that. So to get started, natural language processing as a technique has been around for quite a long time. It's actually been, it's numerous decades, probably the better part of a century, if not more than that. Trying to break it down, this is one of the way that I saw for one of the lectures at Carnegie Mellon University on how NLP works. They have 3 steps here. The first one is acquisition. When I'm trying to acquire a model, I'm trying to learn what a language is, the first thing I'm going to do is take all the language that I can find, combine it with some form of an algorithm, and I'm going to get what I call here a new representation. We'll talk later a little bit more about this. It's actually called a model, a language model. And I can then use that in the next step, the processing. That processing combines the model that I just created. And it uses that to take raw language and turn it into some machine-readable representation of the language. It's a pretty nifty thing, and we'll get later to what that representation means. Once I have this machine-readable representation, I can then generate new language. And that language we can use for any purpose. And you see this sort of thing on your phone when you have autocomplete, or when you have Google, which is trying to automatically guess how you want to complete your next email. So we've had this for an awful long time, right? This has been around for decades. The question is, why are we only now seeing these techniques being applied in real use? All of a sudden now we have a Siri, we have Google coming around with their search engine, we have all these applications that are making use. And the real answer to that is that we are literally swimming in data. And I really want to take a second to pause to appreciate what kind of clip art you can find online. Seriously, I searched for a sea of documents, and I literally got a sea of documents. We are awash in this stuff. You can see everywhere you go, there's enormous amounts of data available on the internet that we can pull down. Project Gutenberg alone has more books than you can think of, and then Google went ahead and added to that, and so on and so forth. But it's not only books, right? We're not only working with written text. We also have code. We've had SourceForge around for forever. Now we have GitHub. We also have Bitbucket, and there's a whole bunch of other ones that are around. Just like we have huge amounts of text, we have huge amounts of code. So with that, the same techniques that I've applied to natural language processing, can I apply that to code? I want to now, instead of just auto-completing my sentence, I'm going to auto-complete the program I'm writing. Well, this was examined by a guy named Hindle, Professor Hindle. All of the slides that I'm going to show, you'll see there's a little tiny line you can't read. It's not meant to be read now, but you can download these later. Those are the references. Generally, they're the references to all the things that I'm talking about here. He has this thing called the Naturalness Hypothesis. And the Naturalness Hypothesis basically says, sure, programming languages are theoretically complex, but practically, we write code the same way we write words, the same way we write prose. We use simple elements, we repeat them an awful lot. Because of that, the same statistics that underlie natural language processing underlie how we write code, and we can use them in this concept. Now, just to kind of help clarify this for you, I'm going to put up these three books. We have a kid's book about going to the dentist, we have a dental school textbook, and I have this website which I found, which does automated reading of dental x-rays. So what's the similarity? Well, they're all containing, broadly speaking, similar information content. They're talking about dentistry. It happens to be one of them is in a representation that's usable by children, one is in a representation usable by practitioners of the field, and one is a representation usable by computers. But they're representing the same concepts. And if you can see this, you start to understand code is really just another encoding of language. It's me trying to tell the computer what it is I want to do. So with that background, right, let's go back to this concept here. I have these representations. Well, what are these representations, and how do I actually get to a representation from a piece of text? Well, so this is, again, from that same lecture I mentioned earlier. These are the couple steps he says, here are the different kinds of representations you may want to work with. We'll start with morphology, right? Morphology is breaking up words into components. I have these things highlighted. What you see on top is Hebrew and the bottom is English. Again, I actually stole this again from his slides. What you can see is one word is not necessarily one word in a different language, or one concept, right? Tifgosh, that word, the one word in blue, means you will meet in English. So there's clearly some sort of a lexical breakdown, which I'm going to have to worry about. So the morphology of the word itself has to be recognized. That's one representation. When you're going to do a lexical analysis, you're going to now do, you guys are probably familiar with part of speech tagging. Maybe you're not. I have to figure out what is this particular word that I'm looking at. I have three examples here, bank, bank, and bank. In different contexts, they all mean completely different things. In syntax, I have to take a whole sentence and figure out how does this thing fit. The example that is commonly used from Groucho Marx when he was playing Captain I think it was Spaulding, in Animal Crackers. One morning I shot an elephant in my pajamas. How I got in my pajamas, I'll never know. So in the NLP textbook, they actually break this down and show how it's a lexical joke, how it's a syntactical joke. Is the elephant in the pajamas, or was he in his pajamas? And by disambiguating that, you're able to understand what he's referring to. When we're trying to make a machine learning system that can perform these tasks, it has to be able to do something like this. I'll just do a quick shout out. Anyone who is interested in really doing a deep dive, and again, this is a pretty deep dive in NLP, the place I got this from is a textbook, SLP, I forget what SLP even stands for, but speech and language processing. It's available for free. And you can download this, the whole book, the entire book, as long as he's still doing a draft of the 3rd edition. It's available free online, so strongly recommended. Moving up one more time, we get to semantics, where I now have a word, but I don't just want a syntactical understanding of it. It needs to mean something. So if I tell my phone, and this isn't a phone, but pretend, hey, Siri, remind me to do whatever, this phone has to appreciate not only what those things go in order, but that it's supposed to do something with that, right? And that's called semantics semantic analysis. Pragmatics and discourse are generally what we refer to when we talk about artificial intelligence as opposed to machine learning. That's when we start getting into real general AI, understanding how these things are used in context. So, hey, pass that over here. Hey, first of all, what does hey mean? Isn't that like the thing you feed a horse? Second of all, pass what and over where? So, you know, that context gets a little bit more difficult. And finally, discourse, where you don't even necessarily have proper sentences. Oh, black is not a sentence. This is not grammatically correct, but it makes perfect sense in context. And trying to get a machine to understand that is difficult. So now that we kind of view this, we're talking about code, right? can this work in code? Well, let's try that. Just so you know, I use a little convention in this talk. The upper right, corner has the language I'm talking about. So here's a piece of JavaScript I wrote a little while ago. And it's just code, right? Well, let's go through the same exact kind of concept. I have symbols. And for those of you who can see, there's brackets, there's var statements, all these things, dots. Each of these are a symbol that I can then interpret. In fact, with code, it's even easier because the symbols are generally very strictly defined. We have lexemes. I have the same word here, time. It's just one symbol. And remember, quotes would be their own symbol, so it's really just time and time. I have to know what I mean and in what context. So the same lexical analysis, the tools I created for NLP will work with code. Syntax, we're probably all familiar with. Those of us who have done programming, you get the dreaded syntax error. But this is actually, again, a benefit. If there's an old joke in Hebrew, ani lo tachat omed. What does that mean? It means I don't understand. There's a word, mevin, which means understand. Tachat means under, omed means stand. So ani lo tachat omed. Even better, there's for those of you who have seen Sesame Street growing up, they have that little thing where the characters are looking at a word combining. And they're doing this with the word surprise. They're going soup, rise, soup, rise, soup, rise, surprise! So in Hebrew, they're doing this, they're just translating it literally. They're going marak, which means soup, orez, which means rice, marak, orez, hafta'ah! And all these, hafta'ah means surprise, and all these kids are like, what the heck? But that's because it doesn't work, right? You have to make sure you understand how it all goes together. In English, it's difficult to make that work. In code, if you don't do it right, the compiler's going to yell at you. So we actually have benefits here. Again, pragmatics and discourse, I do admit I made this up, but I would call that the APIs. We're now going outside of just our local program. We're interacting with the user input. We're interacting with larger systems. It gets to be complicated, and we have the same concepts that we have from before that allow us to do this. I want to actually extend this one more. Let's say we do all this. Right now, I understand what it is I built. I can manipulate it, because if I have that computer-based representation of the code, I can do whatever I want to it. And if I want to insert something, I can. One thing which we will actually not touch too much on, but towards the end of the talk, we'll get to it. There's a way now that I can not only identify a bug in written code using these techniques, but I can actually correct it automatically. Because I recognize what it looks like. I recognize it probably shouldn't like that. And then I recognize what the correct thing should look like. So these are techniques you might all want to play with. So this is the background. What I want to do here is sort of go into a little bit, what are some of the techniques that we use? How do we apply natural language processing to code? And how do we use that to secure software? So the secure software part is at the end. But I wanted to give you this whole background to see where are we standing. And this is, again, it's a deep dive, but I think it's entertaining. If there's any questions, this is a long session, so do feel free to raise your hand in the middle. All right. So there's a paper which is out there, a survey of machine learning for big code and naturalness. Again, he's using the naturalness definition that I provided earlier. The link is down there. This paper is incredible. He did an incredible amount of work really collating hundreds of research papers and going through almost everything you can see on code that's being, ways to process code using natural language processing techniques. It's available online. Anyone can download it. It's not behind a paywall of some publisher. So that's a positive. The way he breaks it down is there's 3 techniques for big code. The first one, as he calls it, is code generating models. It's kind of self-explanatory, but to give it a bit more flavor, it's treating code like text. The same way that I can look at this code as a word and then say, what do I think will be the next word? That's the code generating models. It's just treating code straight up as text. The next one is called a representational model. Computers, modern compilers, they have an awful lot of work that they put into having that compiler understand how does it understand the code. It usually breaks it down into this abstract syntax trees, intermediate representations, machine code. All that stuff can be used, and that's what those models do. It doesn't work directly on the code itself. The last one is pattern mining models. Those of you familiar with the different machine learning techniques, this is unsupervised learning, where you literally just take the code, no previous knowledge, and just say, learn me a pattern. For today's purpose, we're going to focus on only the first one. One thing which I actually have not gotten too much into, and I should have mentioned this earlier, so there's a very, very long history of doing code correction without NLP, right? This is a new concept because we only are now in the time of big code, as he calls it. There's two types that are generally spoken about, broadly speaking. One is called static analysis. Anyone who's ever written code, there's depending on what your IDE is, the same way that in Word, when you have a typo, it'll give you a little red squiggle. There are static analyzers that will just look at your code and give you a little squiggle and say, you didn't put a proper, your syntax is improper, you defined this variable in the wrong scope. Some of them are actually quite intelligent and can warn you about different kinds of bugs. That's one class. There's another class, which as far as I know, is used mostly in the malware analysis field, but it's possible it's used many other places as well. It's called dynamic analysis. Dynamic analysis runs code, analyzes a lot of data that it captures during the running of that code, and then gives you feedback based on that. These are both very, very well-developed techniques. And in many cases, those are really more useful than what we're going to see here. And we're not at all trying to remove those, but we're trying to augment it. So those are very good at finding bugs in code, finding problems with code, and we can do that with this too, and we'll talk about it. Those are not going to be very good at generating new code, because what they're intended to do is examine what you have, not make something new. That's where this is useful, and we'll talk a bit more about that as we go on. All right. So, enough going over the overview. Let's start diving into some of the different kinds of techniques. Engrams is probably, raise your hand if you've heard of Engram models. OK, good, good. So Engrams are pretty straightforward. I want to go a little bit as to the statistics as to why it works. We'll try to keep this very straightforward. So let's say I have a sentence. I made a peanut butter and jelly. Who here can guess the next word? Sandwich, right? It does, the chance that this says, I made a peanut butter and jelly bank, that would be weird. We don't make peanut butter and jelly banks, right? Especially not, I made a peanut butter and jelly freedom. That doesn't make any sense. So you have context here, right? Engrams, what Engrams says is, we're going to remove context from, remove all the context we can, and instead rely on the last n words. So for example, a bigram, 2, right? A bigram would be jelly blank. So if I just had jelly blank, what could I be talking about after that? Sandwich, donut, fish. Actually, fish is interesting because this happens to be a separate, there's a space there. So jellyfish with the space may not work, but you're right, that could go in there as well. There's a lot more all of a sudden. What a bigram says is, and the way you can read that little bit of statistics, the probability of this word, starting at the beginning of the sentence and going all the way up to the previous word, is approximately the same as the probability of the next word given just the knowledge of the last word. So you had that whole thing, and you have some probability as to what that word is at the end for the first sentence. With the second one, you can see they're really not exactly the same. You've really still ruled out a lot of things like bank and freedom, but there's a lot of other options as well. We can get into, though, now why is it n-grams? It's n-grams because it's not necessarily 2. It can be many, 5 grams. Peanut butter and jelly. Is there anything that anyone can think of other than sandwich here? I know I've seen Smucker's sells little jars now of peanut butter and jelly mixed in once. Could be peanut butter and jelly jar, maybe, spread, I don't know. So, but you're really kind of getting, you're scraping the bottom of the barrel. And the likelihood is you're talking about a peanut butter and jelly sandwich, right? In the general case, Engrams are saying, as I add words behind me, I'm gonna assume that the whole sentence is equal to the blank plus a couple words behind it. And n is just how many words do I go back. So we can do this with code. We can do the exact same thing. Let's take this particular sentence. Again, this is a Python example. For I in range 10. Now, I don't know, does anyone here know how to finish this? Say again? And OK, so it could be a colon. It could be a parentheses. It could be a comma. It could be a variable. There's a couple of things it could be. It could be a multiplication if I want to do 10 times something, right? Those of you who aren't familiar with coding, don't worry about it. But the fact is, I can break this down, again, into my symbols. and I can do the exact same analysis. A bigram, I have 10. What could follow 10? A whole lot of things can follow 10 in Python. Let's try to go the 4gram, range 10. Oh, now I've really limited it down. My function only has certain inputs that it can take. So I've kind of brought it down here. A 6gram. I don't know if that actually helps in this case. Well, it turns out some guy did the work for us. Again, the reference is at the bottom. And he found out if you're going to do this, you really only need about 3. About 3 gram, right? 3 words before it. Or I'll call them tokens because they're not really words. And you start to level off. He shows a couple interesting things here. So first of all, as I said, 3 or 4 grams are optimal with both natural language and code. And that's interesting because we're starting to see our first similarity when we're doing this. Natural language and code is really similar. The analysis really, it flows out of all these papers. These really work the same way. The second thing is, notice, I'm not going to explain this too much. There's this thing called cross-entropy. Trying to explain cross-entropy very quickly gets difficult. But the sum of it is, how surprised am I when I see something? You see that language has a much higher cross-entropy, and that's because there's a lot more allowed variability in language. So even after my 3 gram, I'm still surprised a certain amount of time. When I have this with code, though, notice that it's way lower on the graph. And honestly, the units don't make a whole lot of sense, so I'm just telling you it's relatively less, but you're generally less surprised because code is much more regular. So code really helps you. When you're doing this with code, it works better than it works with language. The last thing, which I have another plot for this, but it's worth noting, to implement something like this, you need very little code, 62,000 lines of code. Anyone, for any language you can think of, probably almost, but really any language you can think of, you can get 62,000 lines of code for it off GitHub. Which means you can build this in a weekend. Forget a weekend. Someone who knows the tools can build this in probably about an hour. It's pretty cool. I mean, we're already talking about building a language model for code. So does it work? So what they did was something kind of cute, actually. They said, well, let's try it. We're going to build an Engrams model, right? And what it's going to do is predict the next word. And then I'm just going to implement that as an autocomplete in my coding tool, right? I'm writing code all day long, and then I hit tab. And the same way that if I do that in some word processors, it'll guess the next word for me, it'll guess the next token in my code. And then how frequently is it right? So they built this. They built it to guess the first 2 guesses that the Engram model gave, the first 6 models it gave, and the first 10 models that it gave. The short of it is, oh, I don't have the thing here. The short of it is, it actually worked really well. As you start getting more and more suggestions, you get actually an awful lot of accuracy for it, which is pretty nifty. So they're able to build a code autocomplete using just this very stupid model. All right. Well, as I said before, Engrams has really very little context, right? It's just, what is the previous word? Maybe I can use more context. Maybe I want to know something about what's going on other than just what that string was. So someone else, again, the reference is down there, went to this technique of saying, let's annotate these. Rather than just giving you the actual word itself, let's add some context to say what this thing is. So one of the ways he does this, you see here, len, what's that? That's an identifier, right? I'm identifying a variable. Equal, that's a symbol. And you're going through all the different types of things that are allowed to be used in code. If we were going to do this in English, excuse me, which has been done, it's going to start breaking things down. I have nouns, I have verbs, I have all the different pieces of sentence grammar, which I forget right now because I'm not a linguist. But it's the same kind of context. I'm going to assign these things probabilities based on where they are. In language, in code, it's much easier because in language, as you had from the, time flies like an arrow, fruit flies like a banana. As you have from those kind of concepts, it's more confusing. What they did is they put all these different features into a model, and they built this cool predictive thing. Without going into too much detail, right, as to how they did this, just compare the top highlight and the bottom highlight. The top highlight is the Engram model we just saw a second ago, right? Stupid, dumb Engrams, no context whatsoever. The bottom one is where they added in all this extra information. The top, when they make these models and then have them give 10 predictions regarding the next symbol you're going to see, what they claim in their paper, the Engram one is correct. I think it says 68% of the time, almost 70% of the time. And their additional context added one is correct 80% of the time. So by adding context, and really this isn't too surprising, adding context, you get more information and you can be more accurate. Well, that's a great approach, but some folks recognize there's more you can do with that other than just adding context. Localness. This is actually a pretty cool study. Their thought is code is locally repetitive. And if you think about this for text, text tends to be locally repetitive. If you're reading a textbook and you're in the chapter talking about, let's say you're reading something from my own background. You're reading a human physiology textbook, and you're in the chapter talking about hearts, right? And then later you're reading the chapter about the lymph nodes. The chance that you're going to see heart terminology in the lymph nodes chapter is pretty low, because it's location specific. Code is the same way. And what they did here through this complex chart, which we're going to kind of highlight, is demonstrate this. For Java, if I have a single file, and let's really go only to the very end. If I have a single file, and I look at 10 symbols in a row, so just, this equals that plus that times that, whatever, 10 symbols in a row, the chance that I will see that more than once in a single file, the chance that I'm going to see that more than once is about 30%. It's the 70 minus 1 in the single file. The chance that it'll, I'm confusing. The chance that that'll appear in another file is about 30%, right? The chance that it'll appear elsewhere, it's really only going to appear here. What they do is compare that to English. If I have a 10-word sentence, the chance that that's going to appear anywhere else other than right where I'm looking is 0. Basically 0. Obviously, there's more. There are more zeros after those 2 decimal points, but that's their point. English is very localized. Code is less localized, but it still is localized. They also want to compare and say, if I have a single sentence that occurs with that same 10 words, right? The chance that it'll appear twice in this context in English is 0.2. In code, it's 14%. So I actually have this sort of repetitiveness, and they're showing things are only used locally. That's one way. They define this a few other types of localness. One of them is where you have a function which does appear in many places, but mostly in one. So you see foo is in that last one, and the bar function shows up more in the second one, but not much elsewhere. And they also define proximity. This one I found a little weird, but their general thing was just count tokens between usage of a single term, right? So if I have the phrase, I don't know, I define a function that's get my thing, right? The distance between get my thing being defined and being used, it's going to be a certain number of tokens. Imagine you're just counting words, right? That's going to be small, generally speaking, relative to the whole. It's not going to be equally sprinkled across all my code. It's going to be localized in a certain area. They have a lot of results in this paper. The gist of it is you can see the number 52 and the number 67. The Engram that they ran had 52% accuracy, and when they added this localness element to make their predictor more accurate, it got to 67% accuracy, a 14% improvement. So just the same way that annotating it with information other than just what the previous word was made it more accurate, this is another way to make it more accurate. Okay, that's all fun. But to tell you the truth, Engrams are good for a little bit of stuff, but they're not really sophisticated. The new cool hotness in NLP is this thing called word-to-vec. And honestly, it's not even that new anymore. And this one gets a little confusing because we're going to try to go through this in a little bit at a high level. So how does a computer know what a word means, right? We went through before the different representations. But at the end of the day, how does it actually store this stuff? How can I understand, on a computer standpoint, what this thing is? So there's a couple different options. One is an ontology. For those of you who don't know an ontology, think of it as a ginormous linked dictionary. Every word is present, and not only is it present, it has a link to every other word that may be under it or above it. So color would link to all the colors, ant would link to uncle as well as link to relative, and all those different types of relationships you may have between any word. A plane is a subtype of vehicle, and underneath plane you would have MiG, and underneath MiG you'd have MiG-57, and all those different kinds of concepts. If you think that's a lot of work to make, you'd be right. It's a real pain in the rear to make, and it's very difficult to make it accurate, and every time you want to update it, you have an awful lot of work to do. The problem really is I'm just representing all these words as like, here it is, and here it is, and here it is, and then building these enormous mapping tables. So what someone came up with is this concept: you should know a word by the company it keeps. Represent meaning based on the frequency of other words showing up in a similar context. So what does that mean? Here's 2 usages of the word factory that literally I just did a Google search for books factory. Usually a large-scale factory is portrayed as a product of capitalism, blah, 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 blah. At the Magnetron workshop in the old biscuit factory, Fisk sometimes blah, 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 blah. Those 2 sentences, around them, you have clues to what a factory is. In this case, you can see large scale, capitalism, product, workshop, Magneton, and these words show up. Again, thinking back to that image of people sitting in a sea of documents, if I have billions, and I mean literally billions of pages of text, I really start to get a good representation of what a factory is. Just look at the words surrounding it, and I can go farther out, I can go closer in, but over time I can build a very accurate representation. There's some more math underneath here that makes this not only cool, but efficient. I'm not going to get into how that works here. But over time, you can start to build these pictures of all these different words. Even more interesting, when you start to build these, you start to be able to do, I'll say, general math concepts on words. I'm debating right now how much detail to go into. I'll keep it kind of high level. You can think 2 + 2 is 4, right? So with this, what ends up with word to vec, if I take a man and I add many, I can go to men. If I take a man and I add, if I take a man plus uncle, I can get to aunt. Why? Because it starts to have these words start to take on a mathematical representation. I realize now I'm kind of hand waving a little bit. The gist is this is how the words work. This is how WordNet allows you to represent words in a way that computers understand it. It's all these vectors representing this stuff, and it's honestly kind of neat. There's a very cool image that they show. Do I have it here? Yeah. Oh no, this is a different one. King minus man plus woman equals queen. And it has to do with how the words are presented, and it's understanding these relationships between the words. So let's say I have this sort of nifty concept where these words are kind of placed in this context that I'm able to use. I actually have a link here to some walkthroughs as to how this might work. And it's worth pointing out there's a lot of advances on as to how word2vec works. This was an enormous advance in the NLP field, and it allowed a lot of things that you see in modern search engines, the modern phones and stuff, allowed them to work. So someone had the idea, well, if this can work on documents, why can't it work on code? So code2vec finds vectors. I had mentioned before the concept of a language model. Let's quickly go over that. Sure.
Is it fair to say that this is basically a calculus on top of ontological concepts? Allows you to...
Almost. So it is a calculus, yes. It is not really on top of an ontology. One of the main, for those who appreciate this, one of the main advances of word2vec is that there's a single vector. I don't have a vector for every single word. I have one vector that I learn over all these, over all the documents I search, and then I can work in that context. So there's no ontology underlying it, which is good, because then I can just continue to learn and continue to update the elements of the vector. Okay, we're going to look at this for a second, and then we're going to get back to code2vec, just to understand how it builds. So a language model, we talked before, if I'm having all these engrams, I start to build this concept of, I use the word language model, right? I use this engrams to say how likely is the word preceding this one. Just to walk through this very briefly, here's a piece of word that you might see, a sentence you might see. Roethlisberger is a better quarterback than Brady. That's a pretty safe sentence. I actually had a backup slide where I did a Google autocomplete. Google autocomplete tends to agree with this, which is kind of nice to see. Thank you, call out. This sentence here, colorless green ideas sleep furiously, is a famous sentence written by a gentleman named Chomsky, who was trying to demonstrate I can have a syntactically correct sentence that makes absolutely no sense whatsoever. Right, so it is a syntactically correct, but it is meaningless. That is not a common sentence. You would not expect to see that. Similarly with code, this is something that even people who haven't read code can appreciate. For some variable in some number set, do something, right? This, which even took me a little bit of creativity to write, is not something you would see. It's just random symbols. A language model tries to convert what it sees into what I expect to see next time. It is entirely dependent on the training data. Whatever I give it, it's going to say, look at this, figure out probabilities based on that, and then predict the next thing based on what I've seen. It's entirely dependent on the training data. So how do you use it? You basically build this model from some sort of training database. You have all your code symbols. There's other details present in that data set that you might want to work with, which we'll get to in a little bit, such as maybe documentation. Maybe I have some other elements that describe what I'm trying to build. And the uses I can have for this is either examine the frequency in a current model, or I can generate new code and other things like that. So finally, back to Code2Vec. What I'm going to do is grab a ridiculous amount of code from GitHub. In this case, they were working specifically with Java, right? And their question was, if I only have a piece of code inside of a function, right? Code is generally split up into functions. Those who aren't familiar, you can have functions, and then you call those functions later, and they'll do something. Think of it kind of like recipes if you're not familiar with it. I have a recipe that makes a cake. I have a recipe that makes a donut. And then I can call the recipe to make a cake, donut, make a donut. If I just have the code, that's all I have, can I predict the name of the function that someone would probably give it? And their reasoning was, going back to the use repetitively, I'm training on all this stuff in GitHub. GitHub has a lot of code, so I'm going to build it based on what I have there. People use code the same way they use natural language. They tend to write simple stuff that repeats, which means that if I see a piece of code, someone else has probably written something similar to it before, and I can take whatever they labeled it and come back here. How do they do that? Very quickly, and again, if you get this, great. If not, whatever. Code, here's a very basic piece of code from C++. What this basically says is take two numbers, v1 is a number, v2 is a number, int stands for integer, and return v1 plus v2 times v1 plus v2. Basically add them and square them. Why would you do that? I don't know, but it's what we did. Enjoy. You can break that down into this thing called an abstract syntax tree. This is how the compiler works. It will actually take this code and say, all right, here's the different parts of it. Here's how they all relate. And now I'm going to put them together. So I have two references. I then put those references together with the plus operator. And then I can put that together with the multiply operator. That whole thing lives under the function. The code does that. What you can start to guess from here is if to get from one part of this tree to the other part, I can describe it. So to go from v1 to v2, I start at v1, and then caret means go up. I go up to the operator, go up again to the star, go up again to the function, and then the underscore means go down to the parameter. And I've kind of walked my way through this tree. This is a word. The folks who made Code2Vec decided this is how I'm going to represent my language. This is a single word in my function. You would say, well, why didn't they just use the engrams? This is how they chose to do it. They could have used engrams, but they chose to represent words this way. Turn it into a syntax tree, figure out what all the paths are, and then turn that into a word. Here are all the words that they were able to generate from that really, really simple example. Do this a gazillion times on all the Java code you can find on GitHub, and you start to have a pretty big storybook. And you can build a pretty complex dictionary against which you can compare other things. All right, enough weird things. Let's go to what they have. This is actually their website. I have it again down there. You can check it out yourself. If I have the word login as a function, what kind of things is that similar to? Remember, I'm just talking in terms of code now. So login is similar to logout, authenticate, connect. Why are they able to do this? Because they can look at the word login, say what functions that have the name login, what code do they have? All right. What other functions have similar code to the login function? And what's the name of those functions? So the function login uses, I guess, some sort of authentication stuff. It'll probably hit a user's table in a database. And so does the logout. So does the authenticate. Connect. You can start to see it's getting a little farther away, but you're going to probably need to use a username to connect. And it found that. The thing that everyone absolutely hates from the SATs, right? Equals and oh no, I don't have that one here. They have a this is to this as that is to that on the website also. I don't remember if I actually have that slide. Yeah, I have that one next. I'll get to that in a second. Equals and to lower is the same as equals ignore case, right? So if I have a string and I want to put it all to lowercase characters and then I want to see if it's equal, well, some guy made an equals ignore case function. So is it the same when I'm ignoring the case? That's the same as doing equals and putting a string to the lowercase strings. Here's another one. Receive is to download as send is to upload. Again, they're looking at the words and just saying, what's similar? It's pretty nifty. One thing which I actually don't do in this context is talk about our work. We have some work that's going on right now. We're just kind of trying to extend this and do some work with security and fun stuff. Talk to me afterwards if you want. OK, we've done a little bit of discussion now about NLP, about code, about how this stuff all works. Let's get into the security part. So there's a couple things that I try to touch on here. Honestly, there's more that we can get to. One of the first ones, which isn't really secure code, but I thought it was worth including, machine learning for clean code. Everyone who runs a programming shop knows programming conventions are absolutely critical for a team that's trying to do coding. Why? Because if I can't read your code, I can't take it over later, I can't pass it off to someone else in the team easily, and I probably can't find the bugs in it. So we all need to make sure we code in a similar way. Even if it's something as stupid as putting a new line here, making sure your documentation looks exactly like this, it needs to be present. This is a well-understood programming best practice. There's a technique I can do here. Does this code look similar to the other code in the code base? And here someone went through and did this exact technique. The short of it is they take the code, they put it through, again, just look at other things that have already been put in, make the similarities, and they give you warnings. Hey, this looks like it's pretty different from everything else in the context of the code. I just wanted to include this. They put this in for, I'm sorry, at the bottom they also have, they made this as an Eclipse plugin. Eclipse is a tool for generating Java code. It's publicly available, you can download it. And they made it as a plugin, so you can actually use this thing if you're developing it. I'm gonna give you a warning, it's probably research quality, but it's kind of cool. You can actually take this tool and do something with it. Okay, that's just a fun side. But let's go through the same way we have it before. So there's kind of a couple things we can do. One of them is find bugs themselves. That's kind of neat. But what if I can automatically write secure code? Hey, even better than automatically writing secure code, what if I can actually tell someone what the heck it is I did after I wrote that good code? And to tell you the truth, it would be even better if I could have it get me coffee, but we're not really going nuts here. So the two things I'm going to focus on are those two. But it's worth mentioning, there are techniques out there for automatically writing secure code. And I recommend you back to that paper. He actually writes it in a way where you can understand it, even if you're not an expert in the field. So I do recommend you back to that very first paper with the machine learning and naturalness. So how do they do this find bugs concept? Well, you have a repository of code, right? That's why you're looking at this. Most of your code is probably correct. If most of your code is probably correct, probably you don't have that many bugs. If you only see rare code, the rare stuff that looks similar to the other stuff is probably buggy. Why do I have that if similar to the other stuff part? Because I'm looking for code that looks exactly like something else except for one small part. And I'll give you an example as to what that might look like. Look here. He has this whole thing, and then on the top you see he has that stringify function. Let's completely forget what this is or why he's doing it. But he has this piece of code and it has that line. If you look at the bottom, he actually does not. I'm saying this backwards actually. I'm sorry. You see where he has the word pig type? And then plus value. In the case of in the top one, the word value is not protected correctly. If someone has a bad value in that variable, bad value in the value, sorry. If someone has something malicious in the value variable, you can have a problem here. What they do in the bottom is they have this toString. That toString protects the variable from being used maliciously. If this looks like gobbledygook, really it doesn't really matter so much. The gist is the bottom one has the correct thing there, the top one does not. And what they use this as their motivating example regarding what they're trying to do. Another example that I believe, let me verify this for myself. Yeah, no, it's the same here. So this is the same, what they tried to do. What they ended up using is the Engrams method. And I didn't include the Engrams part because honestly it just gets into the paper, gets a little dense. What they end up doing is the same Engrams model we saw before, where they just look at the previous tokens. If the tokens that they're seeing are almost identical, but not exactly, they call it out for you. And they say, hey, it looks like you forgot something in this particular piece. Are you sure you didn't forget it, or did you mean to? And it just pops up a warning. The person who's looking at it can obviously dismiss it if they used it correctly. But the point is, you may have done something wrong here because this looks really similar to stuff you've seen, but it's not exactly the same. The same researchers did something actually a little different. What they show here, for those of you who can read it, or for those of you who can't read, who don't recognize how to read this code, again, this is in Java, they took the same exact tokens and they shuffled them all around. So functionally, you have a different piece of code. But if you're just looking at this from what are the letters and what are the words I have in this piece of code, it would all look the same to you. And they said this kind of code would be kind of thrown off depending on what kind of unigram model you use and if you use a couple other types of methods. How can you protect yourself from this? So what they end up doing is building this kind of complex thing, but honestly, we've seen many of these techniques before. They take the source files, they parse them into this abstract syntax tree, kind of like the one we saw before, right? They do some mappings to give you some context. And once they do that, they go through, honestly, some fancy pants neural network technique. It's doing the exact same thing. It's doing the exact thing. It's just trying to call out what code have you seen before what code have I seen before that is very similar but not exactly the same? And based on that, I can protect what you have and kind of call it out. I did want to point out, if you remember way at the beginning of the talk, we had the 3 books, right? The kids book, the talk-to-text book, and the code. Those are just translation. And if you look at Google Translate, actually, this is the kind of a technique they use. I have one language, a different language, but it's the same underlying concepts. They try to do the same thing here. I take pseudocode. I want to automatically generate documentation. The same way I can translate English to France, I want to translate code to language. And they go through a technique in this paper where they try to say, how can I do that? I want to say, what is this code doing in English? They had 4 requirements: accuracy, speed, it should be completely automated and on demand. And they went through and tried to do this. The interesting thing that I liked about how they summarized this is they kind of showed the steps that you need to go through in order to do this properly. The first thing you need to do, as we talked about before, is tokenization. Break up all the words in code so that I can find some sort of a translation for it. The second thing I can do is understand what the phrases are. If that's a multiple by, is divisible, and I can start to translate individual phrases by knowing what those correspond to in English. Once I do that, I have a sentence that is not, it contains all the right parts, but they're in all the wrong order. If x by 5 is divisible, sounds great if you're Yoda, it doesn't really sound so great if you're talking in normal context. So then it has to reorder them and put them in the proper order. And the last thing it does is it actually runs it through a language model to sort of add in missing gerunds and because, therefore, and go through there. And they end up with some technique that actually is able to work. It's a very cool concept. Unfortunately, it's incredibly detailed, past the level where anyone would care, rather than saying this application lets you, play StarCraft or whatever your hobby happens to be. It says things like this adds 1 and then subtracts 5 and then does a login. And there's more similar work to this in that paper. Okay, we've kind of taken a nice walkthrough, so let's start to just do a little bit of a summary as some of the stuff that we've done here. So generally speaking, natural language processing concepts can apply to code. That was the naturalness concept that we had at the very beginning. We went through a bunch of different techniques regarding how this works. Some of the very simple ones, engrams, annotated engrams. I didn't talk about skipgrams, but I can even explain it here in 1 second since you've seen engrams. Just skip some of the words in the middle. Instead of looking at them all in a row, maybe skip 1 or 2. Maybe that'll help. And who knows? And it's used, and it's one of the techniques which they use around. Localness measures, we talked about how close things are in a variety of ways. We talked about different types of embeddings, which is really the pretty modern approach that's around. And then we looked at different types of applications that we can use here. We have bug identification, a little bit of code completion we talked about, and document generation. This is kind of a detailed summary as how these are being used and kind of how the field is advancing along. And with that, here's the information that how you can get in touch with me if you want, and I'll be happy to take any questions. Yes?
So at the beginning, you mentioned about opportunities to augment secure coding by potentially leveraging NLP. So we know there is source code analysis that take care of some of those things. So you gave examples about how this could give instant feedback to a developer on saying, you're probably missing this thing. So is this, and you also use the term bug on that. Is that on the context of syntax or semantic?
Okay, that's a great question. The ones that we've talked about here are mostly syntactical. That's the examples because, as with everything with language, that's the easiest one to find. As we're starting to deal with things more like the code to vec and those types, you can start to get a little farther away. And you're going to start to look at things that are in different parts of your code. That is still an unsolved problem. So there is a certain amount of semantic check that can take place with the current techniques that we're describing, but most of it is the more simple, is the local code correct for itself? We're not trying to see are your APIs connecting correctly.
So you mentioned syntax. We're still evolving to the more semantic. What about, have you seen any work pertaining how to translate how to understand from previous documentation of the system, what is the intent of a particular function or the business logic of that system, take that as a context, and then be able to determine, it's not really a problem you're missing a comma or whatever, it's actually that you are missing some boundaries over here, or you're actually missing a validation of a control right here. Really, can this be used in some instances in the future to identify business logic flaw that any of those SAST and DAST tools, they cannot find it?
So my answer to that is twofold. First of all, that's actually work that we're doing right now on our team, which is cool. Part of the reason I wanted to give you this somewhat in-depth walkthrough is to show you kind of where the edge of the field is. That's at the edge of the field. So are we decades away from that sort of thing? Maybe, but we're actually somewhat close to it. If it's decades, it's because the problem's a really hard one. But you can sort of see where we're up to. We are able to understand local code. We're starting to be able to generalize from that to other domains. But I'd say we're still pretty far away from looking at a class and then trying to give the reason for that. However, given that I can now translate between this piece of code and that piece of documentation, and even more so, we were talking about context aware, I can, for a piece of code, I can add the context of the documentation. So now I'm combining, you can think of it as multimodal, right? I have code and raw text. That's something which is, I'm not aware of work that's done that, but that's a reasonable next step for researchers to try to start playing with. So we're getting closer to that sort of concept.
Hi. Just, as you were going through the discussion, I was drawing some parallels with, you mentioned static code analysis in the beginning part, right? Can you just quickly describe some of the differences? Are they doing regular expression checks in some of those products for security versus?
In static analysis?
Yeah.
Okay, my knowledge of how static analysis works is limited, basically. Actually, to be totally fair, so I'm the manager of the team. The people who I hire are all brighter than me, this is why I hired them, are the ones who are doing most of this. I learned a lot of this, and I'm kind of touching base on some of the projects that they're doing that on. That said, the amount that they've passed over to me. So when you do static code analysis, modern static code analysis is pretty complicated. What you're going to do is take a piece of code, basically compile it in real time, see what issues come up with the compilation, and then come back. It's not quite that straightforward, though, because when I'm doing the compilation, I can look for kind of what we were saying before, are things wrong in context? So did I declare this variable that's actually declared elsewhere? Or am I declaring this variable in such a way that it's publicly accessible when I don't want it to be? So it's a combination of we've made an awful lot of rules regarding best practices right? And we've built those into our static analysis checkers, and when it builds all these different representations that the machines understand, it can check to see, is this high-level computer concept present in the representation I just built? It's much more complex than regular expressions, I would say. It's looking to see, based on on best practices that are understood, what's going on. Cool. Thank you very much.
All right. Thank you, Ellie.